A new pathway to engineering quantum materials from within. Researchers have uncovered a more efficient and less destructive method for manipulating quantum materials, one that relies on a material's own internal quantum excitations rather than extreme external forces. By exploiting excitons, short-lived bound states of electrons and holes that naturally arise in semiconductors, scientists can induce powerful quantum effects using dramatically lower energy inputs. This strategy overcomes a long-standing obstacle in the field, achieving strong quantum control without damaging the material itself. If you like my videos, subscribe my channel and press the bell icon to turn notifications on so you keep getting all the major advancements in science and technology. And don't forget to like and share this video with your friends and colleagues. The discovery offers a new route toward designing and controlling advanced quantum materials, potentially accelerating progress in technologies ranging from superconductivity to quantum electronics. Reimagining matter with periodic quantum drives. The idea that light can temporarily endow materials with new properties lies at the core of flow-K engineering. In this framework, a system exposed to a periodic influence, most commonly oscillating light, can adopt electronic states that do not exist under equilibrium conditions. Under the right circumstances, an ordinary semiconductor can briefly behave like a far more exotic quantum material. The theoretical foundation for flow-K physics was laid in 2009, but experimental realizations have remained rare. The difficulty lies in the weak interaction between light and matter. To meaningfully reshape electronic band energies, experiments have typically required ultra-fast, high-intensity laser pulses. These conditions push materials to the brink of destruction, while producing effects that are often fleeting and difficult to stabilize. Excitons as a more powerful and gentler driver. A collaborative team led by researchers at the Okinawa Institute of Science and Technology (OIST) and Stanford University have now demonstrated a more effective alternative. Instead of relying on photons alone, they used excitons as the periodic driving force behind flow-K effects. Their results, published in Nature Physics, show that excitons can induce much stronger band hybridization while requiring far less optical power. Excitons interact strongly with their host material because they're formed from the material's own electrons and holes, bound together by Coulomb forces. This intrinsic coupling allows them to influence electronic motion far more efficiently than external light fields. As Professor Keshav Dani of OIST explains, excitons provide a new pathway to achieving robust flow-K effects while avoiding the extreme conditions that have hindered earlier experiments. This approach significantly reduces the risk of material damage and expands the practical reach of flow-K engineering. How periodic driving reshapes electronic structure. In crystalline solids, electrons move through a periodically repeating atomic lattice, which constrains them to discrete energy bands. When a second periodic influence, such as oscillating light, is introduced, the electronic structure can reorganize. Electrons begin to occupy hybrid flow-K bands, formed through repeated interactions with the driving field. These transient bands alter how electrons propagate and interact, giving rise to new material properties. Importantly, the effect is reversible. Once the periodic drive is removed, the system relaxes back to its original state. During the drive, however, the material effectively acquires a new quantum identity. Why light alone has limited reach. Despite its conceptual elegance, light-based flow-K engineering faces severe practical constraints. Because photons couple weakly to electrons, achieving band hybridization requires extremely intense, ultra-short laser pulses. These conditions not only threaten to vaporize the material, but also limit experiments to very short timescales. By contrast, excitonic flow-K engineering operates at much lower intensities. As OIST researcher Xing notes, excitons enable strong periodic driving without the need for destructive energy levels, making the resulting effects both stronger and more experimentally accessible. The unique role of excitons. Excitons form when an electron absorbs energy and transitions to a higher electronic band, leaving behind a positively charged hole. The electron and hole remain bound together briefly before recombining and releasing energy. During their lifetime, excitons carry oscillatory energy that can act as an internal, tunable periodic drive. Because excitons emerge from the material's own electronic structure, they interact with surrounding electrons far more strongly than externally applied light. Crucially, generating a dense population of excitons requires only modest optical excitation, making them an efficient engine for Floquet band formation. Observing excitonic Floquet effects in real time. To isolate exciton-driven effects from direct light interactions, the researchers used an advanced time and angle-resolved photoemission spectroscopy (TRAPS) system. They studied an atomally thin semiconductor and first applied a strong optical drive to establish conventional light-induced Floquet signatures. Next, they reduced the light intensity by more than an order of magnitude and probed the electronic structure after a carefully chosen delay of 200 femtoseconds, long enough for excitons to dominate the response. Under these conditions, they observed even stronger Floquet replicas, confirming that excitons alone were responsible for the effect. As Dr. Vivek Parekh, now at Caltech, describes, excitonic Floquet features emerged far more quickly and with much greater clarity than those induced by light, highlighting the efficiency of the new approach. Expanding the toolkit for quantum material design. The study demonstrates that Floquet engineering is not confined to photon-based driving. In principle, other collective excitations, such as phonons, plasmons, or magnons, could also serve as periodic quantum drives. This broader perspective transforms Floquet physics from a fragile laboratory curiosity into a versatile platform for material control. By opening Floquet engineering to a wide class of bosonic excitations, researchers move closer to reliably creating and manipulating quantum materials on demand. While practical recipes remain to be developed, the spectral signatures identified in this work mark a decisive first step. As co-first author Dr. David Bacon concludes, the field has now crossed a threshold. The fundamental mechanism is in hand, and the path toward applied quantum material engineering is finally